Good afternoon. My name is Kyle Hanson, and I'm presenting today. I also have Chris Hamm, who is our Vice President of Building Systems and Engineering with me. And I also want to make sure that I don't miss the chance to thank the conference organizers. It's really fun to be in a place where I've been so challenged intellectually and also inspired, as well as the privilege of presenting with you, Chris, and being with you, Lindsey. Thank you so much. We're Timber Age Systems. We make durable, high-performance, modular, panelized homes in Durango, Colorado. The best part is that we often go from the forest to our factory and back into a building in less than 40 miles. So in fact, like everything that we do fits underneath the smiley face that you see up there on the map. I get the privilege of telling you about how Timber Age started. I have an 18-year-old who's in her first year of college. I want everybody to close your eyes and go back and view yourself as an 18-year-old. The very fact that there's not a lot of people in here less than 18 could be something we should probably consider. But think about your 18-year-old self, and would your 18-year-old self be surprised at all about where you're at right now? I know that my 18-year-old self had no stinking idea what I was going to be doing at this point. I graduated with a degree in aquatic ecology, and then I went and I taught high school for a while, and then I jumped over to manufacturing, and I would say that's really what I am. I'm a manufacturing geek that discovered Passive House because of the problems that I'm trying to figure out how to solve in my life, and you'll hear a little bit more about that. The best part about all of those things is I got to work on really amazing teams, and we did really great things together. I had organizations that invested in me, and I had mentors who changed the way that I look at work and life forever. And it shaped the way that I think about what it is to be in a place and to belong to a team. There's a big piece of all of that. I had a virtual mentor, a guy named Andy Stanley, ask this question when he was talking about kind of discovering your purpose in life. And it's not always the same answer, but it's a great question. If you haven't asked this of yourself lately, asking what breaks your heart. It's such a good question because it makes you stop and say, if I'm not doing something on a regular basis that relates back to that, I'm probably not going to be as fulfilled as I could. And that's the interesting thing about this. My professional career had me working around groups of people and being really excited to get up and go to work every day. And the fact that 1 in 3 Americans is engaged in their work, and that our work is like a third of our entire waking, living, sleeping life, that's a ton of minutes and seconds that you never get back. And so for me, I have this thing where I'm I can't believe that I've had this opportunity to be around all these great organizations and neat people who've invested in me and made it a lot of fun to get out of bed and go to work in the mornings. And the majority of Americans don't experience that. It has so much to do with Passive House, right? So when you take a person who's really worried about wasting their life and kind of geeks on business operating systems, I drag my family along with me, and we have goal sessions every year, and we spend lots of time trying to do family meetings and figure out where everybody's going and whether we're spending our time in a meaningful way. And in one of those sessions, I penned what I wanted to do before I die. And I was if I could help create at least 1,000 jobs by the time that I die, I think I would probably have done something meaningful. We're not going to choose. We're all going to go to work. Work is not going away. And so the really fun part is that I think work and place are intimately related. Homes have a tremendous amount to do with whether or not we feel like we're anchored enough to be able to jump in and do something bigger than ourselves. In 2012, I moved to Durango, Colorado, and this is actually my garage right now because my mother-in-law just moved in with us, and we have all of her stuff in there. But it was a great picture to illustrate this. When I first moved to Durango, people were asking me the strangest question, and maybe you guys have experienced this before. The question was, are you renting or did you buy? I was like, what the hell question is that? Why are you asking me that? What they were saying, in not so many words, was, are you going to be here long enough for us to actually invest in a relationship and it be worth the time? And that is, Durango churns. You know, we've heard talk about it's a median house in Durango right now is $800,000. And for people that are teaching and are public servants, the churn is even worse. My kids are 3 years apart in school. Rarely do they get to have the same teacher in the same grade because they just don't stick. And this idea of sticking is super connected to fulfilling jobs. And our ability to help people stick is all about housing. So I can't not think about the environment. I'm just kind of wired that way. So I love the outdoors, and I've spent a lot of time with the Forest Service as part of starting all of this. Where I live, it was not totally apparent when I moved, but it's become more and more and more apparent that the way that we've taken care of forests has failed us. It's failed the next generation. And so now we have these forests that need attention. And where we're at, it's not if the trees are going to die or burn, it's just when. So that what we're trying to solve is the trees have to go someplace. And the worst thing that can happen is they just fall over and turn into carbon dioxide, or a fire runs through and it completely ruins the watershed and the water and the rivers and the utility. I mean, like, the cost of us not maintaining our forests is tremendous. At the same time, and where we live, we've got degreed people, really highly educated people that are working seasonal jobs, or they're working a second job just to try and stick. So there's this idea of, like, people just can't stick, but they want desperately to. On top of that, we've got median earners that are never going to get a house where I live. And so they're stuck trying to figure out how to rent, and then it just keeps getting bigger and bigger and bigger, and then they finally leave. And so we have this beautiful place where I live that is full of very earnest people that can't stay there. Housing is this industry that has the ability to tie together all of those pieces. We have more wood than is needed right next door to where we're at, but we still bring 90% of the wood products from out of state. In Colorado, 90% of the wood products come from out of state. There's got to be a way to take local wood, create fulfilling jobs, increase forest health, sequester carbon, and lower the cost of homes. That would be so cool, right? To create some sort of like fulfilling cycle that just does that. And we're stewarding all sorts of things at the same time. And I think all of us understand that if you're going to spend time trying to think about how to solve a housing problem, why wouldn't you make a really, really good house as you were doing it? That's why I know about Passive House. I was trying to figure out how to make good houses out of a material that I really didn't even understand 5 years ago. And I ended up there. So our mission is elevating communities through innovative materials and methods which transform the way we design and build. It's all about CLT and Passive House, right? Now, what's important is that we have to rally around problems that everyone thinks is worth solving. And then we have to be willing to just take the best tools that we have to do that. Healthier communities, new ways of building, stemming from our best ideas about the materials and methods at play. So you just got the big philosophical introduction, and Chris is going to talk to you about what this looks like in practice.
Thank you, Kyle. So, with the larger mission in mind, the last 4 years have incrementally moved us from one problem to the next. Why CLT? We can use local ponderosa pine. Why modular buildings and passive house? Because we want safe, efficient, comfortable, and long-lasting use. We are here not because passive house is our mission, but it is essential to our mission. Our existence has only been possible through the extensive local, state, and national collaborative efforts with experts in forest management, forest science, wood science, building science, and business development. These collaboratives allowed us to develop a value chain which serves the watershed and to build prototypes validating our manufacturing system. In early 2023, we rolled out the next phase of Timber Age, the Timber Age Modular Building System, or TAMS, as we like to call it. So most of us here are building science geeks, at least we're aspiring to be. We have to consider the efficiency of the design and the operational carbon of our buildings. But too much focus on assembly performance prevents a balanced consideration of the total impact of a structure on the environment. And that total impact is super easy to measure, right? No. Unfortunately, it's not super easy to measure, but we have to try. So one of the more tangible ways that we've chosen to consider this tough idea is to focus on miles traveled per pound. If I can produce structural wood, which is a pretty heavy component, from only 15 miles away, isn't that a little bit better than 1,500 miles away? While we understand the embodied carbon discussion is far more nuanced, and I think Chris can help us out with that a little bit more, I think we can all at least agree we need to start with metrics that are easy to measure. But regardless of the metrics, we need to use both lenses to achieve the greatest impact in the shortest period of time. So a big part of why I'm here today comes from working with Passive House at scale in New York City for many years with Stephen Winter Associates. Modeling the performance of large buildings is critical to facing the climate crisis, but as I'm sure many of you know, the number of variables in the data can be overwhelming. The timeline and the carbon-intensive materials can be very daunting. It left me searching for more control over the process. I began to wonder, how can we build housing quickly enough to keep up with a growing population and do it with a laser focus on energy efficiency and embodied carbon? But also, how can we get people excited and educated about passive house and low carbon construction as fast as possible? Obviously, there's no silver bullet, but after a few months of searching, I came to the realization that CLT, and in particular small-scale CLT production, has the incredibly unique ability to approach these problems and bring together a few of the things that I was already very passionate about. CLT is, we love Venn diagrams, by the way, if you can't tell. CLT is easy to standardize and manufacture with the use of CNCs and modern technology. It lends itself to durable passive house construction. And if done on a small scale, it has the ability to utilize local, low-value trees and aid in our fight against the growing wildfire crisis. This relationship is incredibly exciting to me. But after years of trying to sell and educate about passive house, I've learned that it's time to bring in the big guns if we're really going to move. And nothing sells better than Instagram. CLT just looks and feels good. We now understand the benefits, the health benefits of biophilic materials in our living and workspaces. And when that material has a cool story, is fun to work with and design with, and makes you feel good, that is something that people can really get excited about. So what do I mean by easy to manufacture? Developing a manufacturing process around CLT is incredibly efficient. Our shop drawings dictate how our assemblies go together, but our CNC transfers the majority of our instructions right onto our 5-foot by 10-foot CLT panels. All of our insulated wall, roof, and floor assemblies get built in a similar way. A vapor open air barrier is adhered to the CLT, and wooden eye joists connect the individual panels together. This cavity then gets wrapped with our vapor open weather barrier and filled with 12 inches of dense pack cellulose to achieve about R52. With this level of control and pre-planning, projects get installed and weather sealed in days instead of months, and the efficiency is built into the system and is preserved. Now, there is no wonder why so many designers have chosen to combine CLT construction and passive house. even those who aren't just completely obsessed with whatever the Europeans are doing. Having a continuous thick structure creates a very effective substrate for applying an air barrier and provides an uninterrupted structure for attaching insulation with minimal thermal bridging. But on top of all of that, the ability to utilize wood that would otherwise have gone up in smoke and still touch and feel this beautiful material for the life of the building is hard to beat. This building we recently installed will be the library for students of the Battle Rock Charter School near Durango. The whole building went together in 3 days with windows installed and weather sealed. Barely any trash was produced. And the only stressful feeling we had was that we may have had too many people on site. Needless to say, the students and teachers are ecstatic about this library, but the people who enjoyed it the most were the installation team. And that's not a beer in my hand, that's a seltzer. We also know that our system lends itself to the growing interest in small backyard ADUs. This backyard office was recently completed in Durango after making a quick trip to Washington, D.C. for the Innovative Housing Showcase put on by the HUD, Housing and Urban Development, thanks to funding from the U.S. Forest Service, where we were able to share our story with our representatives in Congress and as well as the general public. Next month, we will be building our first certified passive house, the Hemlock House, that's going to New York. This will also be our first single-family home, but will serve as a model for a simplified structure that could easily be built upon to create multifamily housing. But as we keep mentioning, our ultimate mission is to create affordable housing, which is a great need in both rural and urban areas, as Kyle has discussed. We recently developed the Linear House. That's a fully designed, affordable model priced at $300,000, meant to house a family of 4. Right now, we are working on getting this to be the basis for a 50-unit development, affordable development nearby Durango in the coming years. But our hope is that it could also be a repeatable, replicable design sent to rural communities around the country. So with that, how do we see timber age growing beyond Southwest Colorado in Durango? What is great about our mission that Kyle described is that it gives us some pretty clear direction. So first, our typical plant design is about 5,000 square feet, and it is small enough to go pretty much anywhere. It also needs relatively simple machinery, requiring only about $1.5 to $2 million to get off the ground. As far as where to go, we are guided first by the 32 million acres that the U.S. Forest Service has identified as high-risk fire sheds that will need to be thinned over the next 10 years. They have no idea what they're going to do with all this wood that has to be cut down for us to help deal with this wildfire crisis, which is why they're so invested in what we're doing. For these areas, it is not a matter of if, but when they will burn. And if we don't thin them now and come up with creative ideas to store all that carbon, we are going to just keep digging a deeper hole. And then finally, we are looking to see where this intersects with distressed communities in the United States. Turns out there's a decent amount of overlap, especially when you consider the collapse of local timber industries over the past century. So with that, we believe that this is a problem worth working on, but to create something big, we must start small. And it starts with people. In order to move quickly, we have to learn fast because we don't have decades to keep making mistakes. We have years. This is why we want to keep things small, remain local, reduce risk, learn quickly, and grow intentionally. So hopefully one day our impact can be great. And something Chris was just saying earlier before the presentation was, it's not about scalability, it's about replicability. And that's something that, when he said that, I was like, man, got to write that down. But to also steal another thing from Chris, from his book, Build Beyond Zero, I just wanted to end with this quote. Any intelligent fool can make things bigger, more complex, and more violent. It takes a touch of genius and a lot of courage to move in the opposite direction. Thank you.
Well, thanks for that. That was great and really inspirational. And thanks to all of you for showing up this afternoon. I know last afternoon of a conference is it's tough to drag yourself to your seat again. So I appreciate you being here. I think while my slide deck comes up, I really appreciated the sort of the personal introduction to your story. And I used to talk about this a lot when I started talking about embodied carbon. So I'll do that while we're waiting for the slides. So I come from a background in residential design and build, specifically high performance building and the intersection of high performance building and natural building materials. So for 25 years, I've been building houses out of things like straw and hemp and earthen materials and things like that. And, very early got connected with the passive house community in Canada, where I am, because they were all, like all of you here, the beautiful nerds who were really keen on measuring things and understanding things and improvements. And in my own building practice, we were pretty obsessed with being able to measure stuff. I kind of came into the building industry in the mid-90s, which was kind of the real. There was such a surge of greenwashing in the industry at that point that I realized that I wasn't going to be able to take at face value anything that any product or company or anything was telling me about being green. I was going to need to figure it out and measure it myself. So in our practice, we measured, obviously, air tightness, energy use, the amount of waste that went off of our sites, where it got diverted to, toxins in the products that we were using. Like, we are into measuring everything. And I guess my daughter was probably 16 or 17. She was in grade 11, getting a lot of climate doom in her schooling, and came home one day and said to me, "Dad, like, I know you do this green building thing, and I know it's kind of maybe supposed to be good for the climate, but like, is it really good for the climate?" And so I felt like I could answer her on the operational side of everything we were building. Yes, like, we're building fully electrified buildings. We're using, renewable energy. They're really efficient buildings. But it had already been in the back of my mind that I don't know anything about the climate impact of the materials themselves, like the materials I'm using. What's the carbon footprint of these materials? And so her asking me that question made me think, I need to measure this. And so in 2011, I went to I'm just going to quickly measure the carbon footprint of the materials in our next building project. And however many years later it is from 2011 till now, I'm still trying to measure the carbon footprint of the materials in buildings. It's gotten a lot easier since 2011, but it's kind of been the rabbit hole that I've gone down. And so now that I have slides here, what I'm going to do is just spend a pretty short amount of time running you through at a very high level some of what I've kind of found in the last 10 years or so. The real takeaway here is that, and you guys alluded to it, this is not a trifling part of the climate crisis. This is pretty central to the climate crisis. From what I've been able to figure out, the carbon footprint, the emissions that go into the atmosphere just from making building materials, just for low-rise residential buildings in the US, is about 55 million tons of emissions per year. And that is on the scale of the entire emissions for, some fairly major European countries like Austria, Greece, and Norway. So, collectively, this industry is responsible for a huge pile of emissions. That's also about the equivalent of the output of 13 coal-fired power plants in a year. So, that it's not a small problem. And as the work that everybody in Passive House has done to influence the fact that codes, energy codes, are getting stricter, that the energy grids are cleaning up. If this chunk just sits out as a larger and larger piece as the operational side gets smaller and smaller. And there's some weird animations. So I have been able to do some studies using the Beam tool that Lindsey alluded to. Our team has done several studies. There are, I guess, 4 of them here that I'm going to summarize, where we were able to take as-built plans for low-rise residential buildings in Canada and the US. So we're working, these are actually buildings that have been built. So we know that we're getting a pretty good snapshot of what's out there. I think in total, it's representing about 800 or 900 homes now. So, not a huge cross section, but enough to feel like, oh, we have some idea of what's going on. So between those studies, you can see we did one for the city of Vancouver, one for the city of Nelson and Castlegar, also in British Columbia, one for the GTHA, which is the Greater Toronto and Hamilton area, and then one for a large developer who builds in Florida and South Carolina. And so at a high level, the results showed that at the high end of the embodied carbon for those buildings we looked at, we got anything from 235 kilograms of emissions per square meter of conditioned floor area up to 561. So if you start thinking about multiplying those numbers out across all of the square footage that gets built in North America, it's pretty huge. Interestingly, from all of those studies, the average results clustered pretty tightly together in this range, as you can see, of somewhere between like 150 and just shy of 200 kilograms of emissions per square meter. But we also got some really interesting low results. Interesting because none of these builders, none of these buildings that we were studying, nobody was setting out to make a low or a high embodied carbon building. These are just a snapshot of the way mostly production builders are building right now. And so, it was super interesting to see that in some cases, some of these buildings are much better than average. And in fact, some of them are of a percentage better that they would meet the sort of 2030 targets that a lot of places have. In Vancouver, the best house was 30% less than the average. In Nelson, it was 50% less. In Toronto, it was 40% less. That's where we're trying to get to in the next 5 or 8 years. So there are already builders and buildings that are getting there, but they didn't know that they were getting there, and they don't know why they're there. But the fact that they are there means that there's no reason like everybody can't join at least the sort of the best practice by mistake that some of those low results are showing. So that was sort of, if you add up all the emissions from all the materials, what we're able to see too from this snapshot is that the distribution of where those emissions live in the building, it's pretty common across all of these buildings. About a third of it belongs to the concrete. Somewhere between 15 and 25% belongs to the insulation, and then 10 to 15% on the cladding, and sort of so on up the scale. But didn't really matter what part of North America they were in, didn't matter what level of code they were being built to, that those distributions stayed pretty constant. So if you are a builder and you are trying to think, oh, I should do something about my embodied carbon, it's pretty clear, if you address it in your concrete, your insulation, and your cladding, that's where you're going to. I liked in the previous session the boulders versus the gravel. Our boulders are the concrete, the insulation, and the cladding. Some terminology things that I wanted to show, because I think this is thinking about emissions from materials is new, and you can think about it in a bunch of different ways, and I wanted to sort of run through those with you. One is to sort of just add up the emissions for all the materials in any given building, and there's just a net answer. So usually expressed in sort of tons of carbon dioxide equivalent. And that's great for, when you're trying to do what I did in that first slide, say, all the homes together add up to, this many tons or millions of tons of emissions. It's great for governments to start getting an idea of what their new housing stock is going to be responsible for. Building companies are, going to use that kind of whole building number for their ESG reports. But, it's sort of like saying, well, you can say how much energy a building uses, but a big building might use a lot more energy than a small building. So we can also look at intensities with embodied carbon emissions. One way of doing it is looking at net emissions by conditioned floor area. So those are the results I gave you from the studies in kilograms of CO2e per meter squared of conditioned floor area. So that helps us normalize for the size of the building, helps give some benchmarks and some targets to aim for, kind of regardless of the size of your building. And it does it in a way that prioritizes living space. You could also just look at it by an intensity by total floor area. And that was what we started doing with our studies until we realized, oh, garages and unfinished basements tend to have less embodied carbon because there's less insulation, less finishes, no interior partitions, all that kind of stuff that can add up. And what we realized was, especially in the Toronto region, the houses with massive 3-car garages, if we just did emissions by total floor area, they got the best results. Like you could sort of fool the system by building a whole bunch of useless space at a low carbon intensity. And so we switched to looking at it by conditioned floor area. So, prioritizing living space instead of unoccupied space. And then also, mostly with the city of Vancouver, we also looked at net emissions per number of bedrooms as a proxy for occupants, right? You could make a 10,000 square foot house for 2 people with a pretty good low kilograms per square meter, but it's still a massive house. And so, also thinking about intensity per occupant, I think is another good lens to be using. And so none of these are the better way or the right way or the wrong way. I think it's really important for us to, if you are starting to get into measuring this, measure it in all of these ways. And, depending on what you're trying to solve for, one of these metrics might be better than another. Lindsey mentioned that I was part of the team that developed this Beam tool, which is an estimating spreadsheet. It's free, and it allows you to make a pretty quick and easy and straightforward model of a building. So this is the tool that's behind all of those studies. And I'm not going to talk much about it, but I would encourage you to go access it and play around with it. I also want to be clear that in those studies, we weren't tackling all the embodied carbon emissions that are in a building. We were tackling a bunch of them, but not all of them. So what's included in those numbers I've been showing you is basically the structure, enclosure, and partition materials, kind of everything that's highlighted in green over there on the left. But we did not include some pretty big categories like mechanical, electrical, and plumbing materials, fixtures, appliances, surface finishes, all kinds of things that would actually be adding to those totals. So, when I'm saying, a typical building is maybe 200 kilograms of emissions, that's 200 for the stuff on the left. It's not including the stuff on the right. The biggest reason that we didn't include the stuff on the right is even up until a few years ago, the amount of available data on those kinds of materials was pretty thin or non-existent, but it's getting better all the time. And in fact, about 6 months ago, I did a little track down, tried to put together as much on those missing elements as I could. And I thought, I can start to actually do things like represent mechanical equipment like heat pumps and boilers, ventilation systems, ductwork, wiring, fixtures like toilets and sinks, hot water tanks, countertops, paint and doors, and appliances. And these are kind of some of the numbers that I found for them. I feel like it's not quite robust enough yet to be included in the tools, but it gives us some idea that, there's maybe another 50 kilograms of emissions per square meter that we're not accounting for. So if an average was 200, we're missing, that percentage, that 50. Some of the standouts in the materials that we haven't been counted so far, paint. If you look at that list, paint outweighs all the mechanical and electrical materials. So, that was a bit of a surprise. We don't really think about that. But boy, we put a lot of paint on a lot of surfaces in a lot of buildings. And there's a couple of tons worth of emissions in a normal house just from the paint. So there's lots of work still to do to build all of these things out into the tools so that we're understanding it. I think especially for folks in the passive house world, understanding the kinds of decisions that you're making to reduce the size of mechanical systems. There's an embodied carbon benefit to a smaller heat pump or a smaller boiler, less ductwork, all that kind of stuff. So hopefully, as these numbers start becoming more clear, it'll actually help you be able to justify those kinds of moves, not just from the energy efficiency side, but from the embodied carbon side. Also, in the analysis that I quickly showed you there, all that we're counting is the product stage emissions. So from a full life cycle assessment, we're taking this snapshot from the early product stage. So this is all the emissions that come from getting raw materials, transporting them to a factory, and then actually making products in a factory. There's a whole bunch of other stuff that happens over the life cycle of a product that is both harder to quantify, and also, different players have different levels of responsibility, across that whole life cycle. But certainly for those of us in the design and construction world, thinking really carefully about, everything in that upfront piece. So, obviously we have a lot to do with speccing the products that go in, but thinking about where they're coming from. I love the happy face diagram. The closer you can keep your supply chain to the project, the less you're going to accumulate in terms of transportation emissions, and also the kind of emissions that happen from putting the whole building together on the job site. And then we're working on some ways to represent what I call future emissions, the things that happen from maintenance and repair and replacement and end of life, which, right now in life cycle assessment, those are, calling them educated guesses feels a bit too generous, but they are the best guesses that people who do LCA can make, but they also are, completely wrong, because we actually don't know when somebody's going to change out that flooring or that siding and what's going to happen to it once that happens. So there's, I think, a lot of work to be done in our sort of space to try to figure out how to make sure we're not steering people to make decisions today that have a lot of future emissions, but also not pretend that we can quantify those future emissions as accurately as some LCAs do. However, even though there is, this whole life cycle from the work that we've done, trying to really look at the rest of the life cycle, the product stage in most building materials represents somewhere between like 65 and 85% of that whole life cycle. So I don't feel like it's not the wrong thing to do to focus on that early product stage, because that is where the bulk of the emissions lie. But it would also be good to be able to follow that through the entire life cycle. And then I think for a passive house crowd, starting to put those embodied carbon numbers next to operational carbon numbers is where I really hope you get inspired to start thinking about embodied carbon, because these are some results from the study that we did in Nelson, BC, where they gave us the house plans, but they also gave us the HOT 2000 energy models that the buildings had to submit for their building permit. So we had, HOT 2000 is not a great program, but we had some idea from HOT 2000 what their operating emissions would be. And so you can see on this little graph over on the left, this is the average across the 35 houses that we looked at in Nelson. And the split is almost even over the first 20 years of the home's life, the dark blue being the embodied carbon that happens from the materials. And then the light blue, the little slices are 1 year each. But that total light blue bar is 20 years of operating emissions. So in general, over the first 20 years, it was half and half. But you can also see as you sort of move across, we found several examples where both the operating emissions and the embodied carbon were high. And so that's obviously terrible, and we want to avoid that as much as possible. The next one over, that's called mixed one, that was actually a reasonably low embodied carbon building, but it still had terrible operating emissions. So, the fact that the embodied carbon was reduced some doesn't really make it a great building for the climate. Mix 2 is really interesting because it was basically it was a passive house. It was all electric. BC's grid is really clean, so you can see the little light blue bar is almost gone because it's pretty much a zero emissions house. But at almost 50 tons of emissions on the embodied side, it's actually worse than average for that area. And then on the far right, where you get both of these things right, where you can reduce both of them, that's where we want to go. And so I think it feels like one of the next steps in the practice of doing passive house is starting to add this dark blue bar onto your analysis and make sure that you're not doing the thing of like, oh, I knocked all the operating emissions off of this house, but I did it at the expense of a huge amount of embodied carbon. Really, we want to make sure that both of those things are as low as possible, and that's how we win. We did a really interesting study for Doug Terry Homes, which is a production building company in Ontario. I think they do about 500 homes a year, so they're not massive, but they're not tiny. But it's a great example of sort of the insight that an embodied carbon analysis can bring to a builder. So, we took one of their models and we did the embodied carbon as they build it, and they build several hundred of these a year, and you can see it was about 66 tons as built. And then we used the beam tool to kind of iterate on that design. So we changed nothing about the design, the shape of the house, the size of the house, all of that stuff stayed the same. But the first thing we did was just identify for them, hey, there's a bunch of insulation materials that you use. You're using the highest embodied carbon version of that product. And if you just switch to the lowest embodied carbon version, there's 20% reduction on the table for you. So there's no difference in how you're assembling the house, even what material you're buying. That's like a procurement choice could make a 20% reduction. We then, what they wanted to know was, in the next 5 years, if we were to switch a whole bunch of our products to the best things that we could switch them to, where could we get to? And that's the one that's highlighted. We called it the one-to-one substitutions. And you can see we got it down to just under 23 tons of emissions. So that's a 65% reduction from there today as built. And again, that's just straight up product swapping, but not, this is more like, switch from your mineral wool bats to cellulose. It's switched to a lower carbon concrete mix. So, not things that are way out of the realm of possibility. Everything we tried to do for them in that one-to-one substitutions would sort of had a cost parity. Everything was available in their Ontario market. So, very achievable. And like you can see there, about a 65% reduction. And then, on out into the future where, we start suggesting things that either the products are less available, maybe don't have their code compliance stuff in line yet, a few small design changes. But again, pointing them to the fact that, within 10 years, they could actually have a zero embodied carbon home, which, they were the first Ontario production builder to be doing all net zero homes. And so, they could be at that level on embodied carbon with some foresight and planning. And so, for those of you who are in the business of helping kind of inform builders on how they can decarbonize, I feel like the embodied carbon thing, it still kind of freaks people out. They're like, oh, I don't know what to do. I don't know what products to use. It all feels really overwhelming. My strategy is what we did with Doug Terry and other developers we're working with is like, you know what? Just find one thing a year that you can reduce. Like, we still have, it's 1 year less since I made this slide, but 6 or 7 years before 2030, if you want to get a 40% reduction by 2030, you're only looking for a 5% reduction in your embodied carbon every year. And that's really achievable. Talk to your concrete supplier. For sure, you can knock 5% off your total embodied carbon emissions by speccing a better concrete. Look for a better insulation, find the best in category drywall product. These sorts of things, I'm not trying to make that list as a prescription, but, just trying to point out that these are really approachable changes and that nobody, needs to go find 40% at once. You can find it piece by piece over time and still make a really big difference. And I'm just going to end with a couple really quick case studies. Happy to talk more about these with folks after, but these are just a couple examples. I chose these two because they both are passive house buildings. So, we know that on the operating side, they're both electric and passive house. So, they're doing as much as they possibly can on the operational side, but these are projects that we're getting really great results in terms of their embodied carbon. So this set of 4 homes in Phoenix by Valley Homes, their embodied carbon was 59 kilograms of CO2 per square meter. I don't know if you remember back to the early slide, but 200 is an average in North America, and the best result we saw in all of our studies was 72. So 59 is really exceptional that way. And then New Frameworks, similarly, it's a passive house, and they had this house at about 31 kilograms of emissions. So there is lots that's possible, lots that's feasible, lots that people are kind of putting into practice right now to get some pretty huge reductions in embodied carbon. And the embodied carbon space right now is where passive house was 20 years ago, with most of the industry going, you can't drop it by 80%. And everybody in passive house going, yeah, you sure can. And everybody saying, oh, but it's going to cost more. It's going to, all the stuff. I'm hearing exactly that same conversation now around embodied carbon. And I'm saying, here's somebody who is getting an 80% reduction. They did it affordably. They met code, all of that stuff. The arguments are pretty cyclical, but I feel like embodied carbon now is sort of where passive house was maybe 20 years ago. So, if we were able to kind of get to the level that Valley Homes and New Frameworks are doing, we're talking moving that total number for the US from 55 million tons down to about 13 million tons. That's like shutting down 100 gas-fired power plants. So, that's no small impact on sort of the national emissions picture. It's pretty big. And, I think it's well within the wheelhouse of anybody who's been in passive house, who's kind of into numbers, into measuring, into, figuring out how to optimize. I feel like diving into embodied carbon would probably suit your personality type. And there's a lot on the table right now in terms of what we can do for the climate if you do dive in and do that. And I'll just end by saying that the project that I'm working on right now is with ResNet, and we are coming up with an ANSI standard for actually measuring embodied carbon, specifically in homes, and to do it in a way that works for energy raters. I think in the home building market, whether you're doing passive house or HERS ratings or using HOT 2000 up in Canada, energy modelers are making exactly the kind of model that you need to do an embodied carbon study. There's not much more information that you would need to put into that model in order to get some really good embodied carbon numbers out. And what we're trying to do is get a standard out there quickly so that no matter what way you're looking at the energy modeling of a building, the way you would approach embodied carbon works in that workflow, but is also the same across all of the different energy rating systems. And I think if you want to dig into any of the studies that sort of informed any of this work, there's a bunch of studies and references you can dig in and get in there in more detail. But I think that's what I've got for you.
Should I just use this microphone? Oh, that one. Okay. Okay. How about now? Great. Thank you. Thanks so much, you guys. We have some time for questions. I have a handful of questions that I'd like to go through. And this first one is to all of you. I think for some of us in the design profession, coming from a background from architecture or engineering school, or maybe as a developer or a homeowner, a potential home builder, how would you characterize, like, what are the important things that makes a low carbon material a low carbon or a carbon storing material?
I guess there's a certain gut check you can do with materials. The product level emissions that I was talking about come from manufacturing. So if you know how something's made, if you had to melt rocks, there's probably a lot of embodied carbon. If you had to melt ore, there's probably a lot of embodied carbon. Like basically, if you think about it, did it take a ton of fossil fuels to make this material? Not surprisingly, the embodied carbon is probably pretty high. Less maybe obvious is there's a whole bunch of materials where a chemical process happens in manufacturing the material that's really GHG intensive. So a lot of plastic and foam products, it's not that it took a lot of fossil fuels in the production, but in the production, a whole bunch of chemicals were released that are really potent greenhouse gases. The reason concrete is such an intensive material is it's got both of those, right? You have to heat up the rocks, so there's a lot of fossil fuel burning to heat up rocks, but then what you're doing by heating up the rock is busting all the CO2 that was in the rock out of the rock to change its chemical composition. And so, it's emitting a whole bunch of CO2 directly as well as through the fuel use. So, the intensive ones are from those processes. The carbon storing ones are either from the carbon is stored in the material from photosynthesis. So if it comes from a plant, whether it's a tree or a rice husk or a stalk of straw or a hemp fiber or anything like that, those plants drew carbon dioxide out of the atmosphere, and in the short life cycle of the plant, that was going to go back into the atmosphere. But instead of letting that happen, we lock it up in a building for some time. Those are kind of the carbon storing ones. Wood and timber is a tricky one. Anybody who's looked at the beam tool, you'll see that we don't actually attribute wood with any carbon storage, not because there's not a whole bunch of carbon atoms in the wood, there definitely is, but because I don't know, and we haven't been able to find the science that tells us, is the fact that wood is in my building helping the climate? There's a lot of questions around wood that are different than all the other biogenic products because trees are so long-lived, and because when you cut a tree down, there's a bunch of carbon in the tree, but if you had left the tree, it might have grown for a lot longer and continued to be a carbon sink. So there's sort of like a lost carbon storage opportunity. And also, we're not particularly good at getting all of the carbon from a tree into a building. Like typically less than half of the total carbon in that tree, especially including in the root system, which just gets abandoned in the soil. If less than half of the carbon that was in the tree makes it into the building and the other half goes back to the atmosphere, you maybe didn't do something great for the climate. I think the way that you're doing wood calls that into question. And I think we need a lot more science to sort of say, like, when is wood helpful and when is it climate positive and when is it not? And I think taking thinnings or other sources of wood that weren't going to be long lived and that may have gone back to the atmosphere due to fires or whatever, there's probably a strong argument for that. Mowing down lots of good old growth timber is not going to be good for the climate. So I think we need to work on figuring out how do we identify the products that are and aren't. And from what I see in what you're doing, it probably is climate positive. But there's a lot of wood products that I would say aren't, and there's a lot more to figure out there. Is that a reasonable answer?
Thank you. Yeah. Yeah, I really want to hear a statistic that you told me when we were planning this.
Well, so one interesting thing, maybe just related as you were talking about this, is that out of all of our national forests, 30 years ago, they were all carbon positive. They embodied more carbon than they released. And now 70% of the national forests in the United States emit more carbon than they actually consume, which is just a crazy thing to think about. And then the other one that, it's like, when you asked that question, I was like, I had a conversation with Johnny from 475 earlier, and I was like, one of the reasons why we're always wondering about using things from Europe is because it's hard for us to know exactly how much carbon is tied up in transporting all the things. And he was like, actually, we've been thinking about that. We've measured it. And so the other answer to your question that I think is really important, and part of it is why we are so focused on local, is if someone can tell you the story from beginning to end, it's probably worth trusting, or you can at least make a better decision. If there's 7 handoffs and no one is thinking about it, in some ways I start to get super pessimistic about whether or not they really understand what's going on. So I think the ability of someone to be able to tell you the story of the material is probably a great way of being able to test whether or not it's going to be something that you could trust or use.
Thanks. I think that's all really helpful to just help us like have a sort of really basic common sense understanding of what we're trying to do. Concrete is the #1 emitter. To many of us, that feels daunting. And from my personal perspective, working in a rural area, which a lot of the American West is, do any of you have any advice on how to get a better concrete spec and actually into the building?
I have some thoughts. I mean, I think, yeah, concrete is daunting. And I mean, #1 embodied carbon strategy is use less, right? Whether that means make the whole building smaller, whether that means use slightly less of the material. So for concrete, it could be, I was kind of stunned to find, I forget who I was talking to, somebody in Massachusetts, and a concrete basement wall in a house in Massachusetts is 10 inches. Where I come from, it's 8. And it's like, if 8 is good enough where I am, like there's 20% of the embodied carbon you could drop from your concrete just by making that wall a little thinner. Could the building go less deep in the ground? So, the first 4 feet are concrete and the rest is framed above that. So, there's a whole bunch of just reduce the amount of material. So that would be the #1 strategy. And then it's getting more and more common to be able to order a lower embodied carbon concrete. SCMs, supplemental cementitious materials like fly ash and slag can go into concrete. It sort of lowers the carbon footprint. There are some great innovations kind of just coming to market where the actual formulation of the concrete is different and the emissions are a lot lower. We're in the realm here where Prometheus Materials has their first CMU plant. They have a CMU that's getting pretty close to 0 embodied carbon in that particular product. It's an algae-based concrete. There's a lot going on in that space. I think we'll see 5 or 10 years. Concrete may not be the offender that we think it is now, especially in our smaller buildings where, you don't necessarily need the extreme high strengths that you do when you're going up, lots of stories. I think I get excited about the sort of low scale residential world because I think all of the low embodied carbon and carbon storing materials will get their launch in the low rise residential space because it's just easier to experiment in that place. The barriers to entry are lower when the buildings are smaller. So I think, yeah. And then also think about buildings that don't use concrete, especially when you start thinking about resilience. There's a lot of places where being in the ground isn't the best strategy. So things like, pier type foundations, especially screw pier foundations, like just get the whole building out of the ground and suddenly there's no concrete in the building. That's a really great way to, there was a building in the Nelson study. Well, it didn't get included in the study, but he brought us his results just as we were finishing. And it was a zero embodied, well, it was 2 kilograms of emissions per square meter. And it wasn't different in its construction than some of the other things that were at the low end of that study, but he did it on a screw pier foundation. So he had no concrete. So suddenly, his numbers were just way better, even though the rest of the building wasn't that much different than all the ones around him.
Do you have experience with that? Would you like to add to it? No. Okay. That would be a hard one for me to add.
We'll mention that, yeah. So that ADU that we were talking about before, the backyard ADU, that's built on those screw piers. So that's something that, works really well, again, with lighter, smaller construction, something where you can actually use glue lams or other sort of wood-based foundation structure to make smaller structures. So we definitely see a lot of interest in that right now. Again, the 80 market specifically, but yeah, going, like you're saying, going smaller makes it a lot easier to test these things out.
Okay. When we were talking earlier, you mentioned the cost of a typical CLT manufacturing facility. And I'd love to know just a little bit about how you are getting yours so much more approachable.
That's a great question. So the biggest thing is that we make smaller panels than most manufacturers do. A lot of the manufacturers in North America can make 30, 40 foot long, even bigger panels of CLT, which are often much thicker. And that's obviously very useful for larger buildings because you can span greater distances and make bigger floor plates. But we actually designed our system around this smaller scale residential model. So our panel is 3 inches thick, and we do 4 foot by 10 foot or 5 foot by 10 foot panels. So that again, change in scale allows us to change a lot of the equipment that's required. So there's certain pieces of equipment in large CLT manufacturing that are incredibly expensive and can take years to source, and that's part of why people think it's taken a long time for this technology to catch on more in North America, because it is so capital intensive. So there's, for instance, one thing is a finger jointer. When you want to make a 60 foot long piece of CLT, you need to finger joint individual boards together. That is a very particular piece of equipment that takes up a lot of space to make take reasonably shorter boards and make them into really, really long boards. We don't need that because we just get 11 foot logs and we can make a 10 foot board. So that's one thing. The other thing is we do what's called a vacuum bag press, as opposed to a large hydraulic or pneumatic press. So again, that's something that we designed and built ourselves. Cost us around $10,000 or something like that. And one of these presses typically, can be millions and millions of dollars. So I think generally most CLT manufacturers, to get up and running, it's going to be anywhere from $20 million up to $100 million to get a plant started up. So again, that's a big part of the model that we're trying to create to make it replicable, something that could potentially go anywhere.
I have so many more questions, but I think I should give the audience a chance to ask some. And there is a helper with a microphone who will bring it to you.
City and County of Denver. Thank you for the presentation today and the discussion that we're having. I did want to make one quick shameless plug for creating one fulfilling job. There is a embodied carbon position posted today on my team in Denver for embodied carbon policy and education. So just let me know if you're interested in that. If you know someone, that would be great. But my question is for Chris. What do you see are the biggest barriers for progressing embodied carbon policy at a national level?
Well, I think a standardized way of doing the measurement, which is why I'm putting my focus into trying to create that standard, because until you can measure and compare reliably, it's going to be hard for a policy to be implemented. You're going to need somebody to come to you if you're going to say, here's an incentive for going below this amount of embodied carbon. Somebody's going to have to show you that in a way that you feel is trustable and replicable and comparable to somebody else who's applying to the program. So I think measurement is a big one. And then, data quality is still a bit of an issue. It's far from every product that's out there that actually has an EPD where you can see that value. So a lot of times in our current modeling, we're using either an industry average, or we're averaging all the products in the category to represent a particular product that doesn't have an EPD. So there might be 8 competitors, 3 of them have EPDs, 5 don't. So we're kind of using the 3 that do to represent the 5 that don't. But one of those 5 might be triple the carbon footprint of the other ones, and the other one might be a 10th. So there actually are ranges like that within product categories. So it feels like, we can kind of point to maybe a middle ground, but we can't be, fully accurate until there's more data. But I think that the standard for measurement is the biggest hurdle.
I would like to point out that the winner of the detail competition and the Passive House Awards last night won because it was a detail that showed how to build a building without a concrete floor slab. And it had an engineered wood slab on top of low carbon insulation that was a beautiful detail that anyone could use. So I wanted to point that out first. I'm really impressed with the way you're setting up flying CLT plants, these little CLT plants, and the way you're doing it. My fundamental problem is that CLT uses 4 times as much fiber per square foot than conventional, wonderful, lightweight, light wood framing. And I'm wondering, in a low building where you don't need that strength of that 3-ply CLT, whether it makes sense to be using so much fiber.
I think it's a great question. And I think it's really hard to defend to use traditional CLT, where it's changed hands several times, and the source of the CLT is a variable priced lumber market. From a passive house standpoint, one of the things that I think is really interesting is we're not doing, yes, there's more wood, and that's the problem we're actually trying to solve. So it's really difficult for us to figure out how to actually use the amount of material that needs to come out of the forest, because it's not like it's 15% extra. If you look at a native ponderosa grove, the distance between trees is 150 feet, and right now in a lot of the ponderosa bands that we're dealing with, it's 10 feet between trees. And so much has to come out that actually a really dense product helps us in terms of the forest treatment goals. From a building science standpoint, the ability to have a monolithic layer with a really, really predictable, a transference rate and hydrothermal buffering that you don't have to paint is a beautiful way to build a house, because you start out with this thing that buffers and controls air movement. And then all of a sudden, you don't have to think about it anymore, and you don't have to manage for all of those gaps that are created in a traditional building. part of what we're trying to do is make it easy for builders to be able to put up a passive house. That's a big, like, if we could have someday every person that uses our system uses it because it's much easier to build with. Oh, and by the way, it's passive house performance. I feel like we won. We're not selling passive house, but we're actually not selling anything that couldn't be passive house. So we're trying to take away the choice. And just watching builders and how hard they struggle with controlling air movement and all those kinds of things, we're trying to give them a system that helps address that problem at the same time.
I think that was really well put. And I just want to add that you kind of mentioned, but again, we looked at the example Chris showed, and the paint was the highest carbon aspect of that study you did, and I don't think that included drywall. Not sure, but the fact that our walls also don't need to have drywall or paint put on them just adds, even though it is more structural material than is required, the fact that we are, again, solving that problem of trying to find a way to store all of this wood and getting rid of those other elements, we think kind of helps add to that as well.
All right, that's our time. Thanks everybody for your great questions and for your wonderful, terrific answers and all the work that you have done.